Hello Professor Balaji, hello Sachin. Today in this video I'm going to cover the 5 concepts that I have learned from the data mining course. Also because SAS runs on cloud and due to time constraints I have made a Word document which has the screenshots of all the results of the concepts that I want to explain. So let me explain with the help of that screenshot. So here the first concept I'll be explaining is ensemble. What I've done here is I'm explaining ensemble with the help of with reference to the output of model comparison. Now here to both ensemble and model comparison I have given two models as inputs, neural network and decision tree. So when we run this, the results that we see are as follows. This is the result for the ensemble and there is one more output for the model comparison. So when we run that, this as the output for model comparison. So let me explain with the help of the document. So here we can see that there is difference in true positives and true negative numbers for ensemble output and the model comparison output. We can see that for ensemble result as clubbed for the training and the validation set for neural networks and the decision trees. This is for the training set and this is for the validation set. These are much better results as compared to the model comparator output. Also for misclassification rate and the errors, if we see for maximum absolute errors 0.435 for training, so maximum absolute errors for model comparison we get 0.13 and 0.9. So this 0.43 is much better than these numbers. Then we have 0.92 for validation set. Maximum absolute error is 1 and 1, which is again less from compared to 1. Then for test set we have 0.90 and here we get maximum absolute error as 1 and 1. So again this is less. So we see that the output for ensemble, but the errors are much lesser as compared to model comparison, and same for the misclassification rate as well. When we see the cumulative lift curve and the lift curve for model comparison and the ensemble, we see that for ensemble the lift is much smoother, and for comparison output we see that decision tree curve is at a much lower level as compared to the ensemble output. There is more lift in the ensemble output. The second concept is information gain and lift curve in classifiers, and I've picked decision tree for it. Here we can see that important variable is middle mean square. And since it is the most important variable, the splitting for the decision tree has been done on the same. So let me run the output of the decision tree and then we'll see the results. This is the output. As we can see, middle mean square, which was the variable with the most highest importance, was split first, and this gives the highest information gain. Entropy is a measure of disorder of a node, and as information gain increases, the entropy of basically lift curve is used for target marketing, and it does not tell us the profit in this case for decision trees. And then the following is the lift curve. In classifiers, the curve will generally rise at the start and then it will trend down the curve to 1. The lift curve and the gain both have maximum values at the start. As we can see, 15.96 and lift is 1.15, which gradually reduces by the end of the curve, and we have 75% response, which is the highest at the start, where the gain and the lift curve is the max. Third concept is trade-off between complexity and the error rate. So in a decision tree, when we increase the complexity, the rate of error reduces. As you can see here, we are increasing the depth of the decision tree from maximum depth 3 to maximum depth is 6. So as we can see here, after increasing the depth, the misclassification rate has reduced from 0.288, 0.25 to 0.173, 0.149. And similarly for the errors, 140, 500, it is reduced to 95, 96. So we can say that as the complexity increases, the error reduces for decision trees. The fourth concept is concept of overfitting in decision trees. So what happens here is when we increase complexity, the error reduces and the accuracy increases. But doing this is an issue, as we increase the complexity to a greater extent, this gives rise to overfitting. What we mean by that is, as the models get too complex, the accuracy increases on the training data, but the increasing accuracy, the training set and the holdout set diverge in terms of accuracy. The error for the training set reduces, but the error for the holdout depth, that is the testing set, it will keep on increasing. So that does not generalize. So this is another concept, and to reduce this, we should avoid increasing the complexity to a greater extent, and we should control increasing the complexity. To avoid this, we do pruning of the leaf nodes, which does keep the error in check and also the complexity in check. The fifth concept is concept of global optima, learning rate and momentum with respect to the error. Here for both the flows, I have taken multi-layer perceptron and I have kept the number of hidden units. And for optimization, taken backpropagation, maximum iterations 20 and maximum time 4 hours. It will not take so because it has just 1000 records. And what the difference here between these two is that for one I have kept learning rate and the momentum as 0.1, and for the above one we have kept it as 0.9. So the only difference between these two is that the learning rate and the momentum. Let's see the output. This is the output for learning rate and momentum as 0.9, and this one is the output for learning rate and momentum as 0.1. So we can see that with 0.9, this is the global optima, and this is a weight at 2, and with 0.1, the weight is found at iteration 20. And as 20 was the maximum iteration, this one is the better one, which is the iteration 2, and this was for a learning rate as 0.9. So learning rate has 0.9, which is high, gives higher learning rate of the weights, and it also gives lower errors. As we can see, for higher learning rate, we have lesser sum of squared errors, lesser values for the misclassification, and also lesser values for maximum absolute. Hence, we can see that learning rates and momentum give us better optima, global optima, and better error rates.